Okay, so I'll do it with the headset. Okay, so thanks for the introduction, Hassan. So hi everyone, I'm Tal Kolan, I'm from Intel. And I've been in Intel for around 15 years, and I've been working on pre-silicon verification for hardware and firmware. And definitely proud.
Last interruption.
Yeah,
If you can bring your mic a little bit closer, so we can hear you clear.
is it better now?
Much better. Thanks, and sorry for interrupting.
Okay, so I'll continue. So I'm definitely proud to be part of the Intel Core design team. And since 2016, I've been leading the development of machine-based solution for verification. And what I'm going to share with you today is our journey, basically our story of how we develop machine learning-based solution to verification and integrate them into the verification environment. This story has successes, it has failures, it has a beginning. We are yet to see its end. This is a story that is still being written. And it's a story about evolution of how verification team and an AI team without any prior knowledge on each other domain came together and joined forces, and together, step by step, we succeeded to bring more and more value to verification with our solutions. And I'm sharing this story with you in the hope that it will inspire other validation teams in the industry to adopt machine learning for the processes where they see the value in it. And I think that as an industry, it will have more traction in this field, and we will get bigger support and more solutions from the vendors and more academic works. I think this will help the industry as a whole. And with that, our journey begins. And so, like every good story, it starts with an idea. One person who saw a problem, he had an idea on how to solve it, and he tried to tackle it. And this is how Cliff was born. And basically, the problem that this person saw is that we have hidden bugs due to lack of verification. And how this was presented is that in verification process, we run many, many thousands of tests every week or every day, and some of them are failing, and that's fine. We are debugging them, we're finding the failures. But most of them are passing, and then we are asking ourselves, are those passing tests present frequently validated functionalities or rarely validated functionalities? Because if we have some functionalities that are rarely being covered, then they might have hidden bugs. They are not well validated, but not well enough validated. And so we want to see whether we can stress those rarely validated functionality to find those hidden bugs. And we need to do that without extra human effort because we don't have enough resources for that. Now, let me define a bit what is the rare in our case. The rare coverage event for us is something that was hit between 10 and 200 times. And more than 200 in the last 4 weeks. And more than 200 is basically something that we are considered frequently being validated and well validated. And less than 10 is just not enough for machine learning, not enough samples. And so the idea that this person has is to automatically create new tests for these rare functionalities using machine learning. And the solution was quite simple. Take all those thousands of random tests, learn the log files, and run pattern recognition algorithms to learn the relationships between the test inputs and the test outcomes, and then use the recommendation out of this algorithm to run new tests and stress those rare functionalities. And I have to say, even after 5 years, when we first introduced the solution, Cliff is still finding unique bugs today in our designs. And this includes Alder Lake, which is just launched, and the latest Intel under development CPUs. So let's take a bit deeper look at what is the Cliff pattern recognition. So we'll do it with a small illustration. So let's assume we have a small data set of 8 tests. And for simplification, we only have 2 input knobs to our test generator, knob A and knob B, and both of them are Booleans. And so they can randomly get values of true or false. So in this data set, you can see that the chances of us to hit the target X is 50%. But if we look only on the data set where B knob is true, then our chances to hit target X are 80%. This means that the target where knob B equals true raises our chances to hit target X from 50% of random values into 80% with this specific pattern. And this is basically what we do with pattern recognition. Now, this is nice on a simple example like that, but when we go to the real full scale of a core design, when we have 10,000 knobs and 10,000 targets and 100,000 seeds every week, this is not something we can handle with a small table. This is something we need machine learning for. And the way we solved it is by incorporating an ensemble of algorithms. it wasn't just one solution that fits all. So we had all types of rare functionalities that we needed to target. And so we used an ensemble of solutions to try to target and optimize the solution per rare event. And I'm going to deep dive a bit about the one in the top, the random forest and the feature importance, just to explain our approach. So in random forest classification model, we basically take all our features and we randomly select some of them and build a decision tree. In this case, our features are stimuli events, and they can either happen in the data set or not. So for example, A is one of the stimuli knobs that either happen in the green line, or if we go in the red line, it didn't happen. So in this example, the path where A happened and F happened in the data set cause us to hit the event, while other paths cause us not to hit the events. And so we build all kinds of trees because it's a forest, and each of them is randomly selected a different set of features. And then we use this model to understand how to predict whether a test will hit the target or not. But in fact, that's not how we want to use the model. We don't want to now get a new test and ask ourselves, does it hit the target or not? We want to understand which of those features can help us best hit the target more, right? So we want to take all the features that the model give us, basically doing like reverse engineering of the features, and do feature importance on top of them to get the subset, the pattern that help us to reach target the best. If we look a bit about results of Cliff, Cliff from the get-go was a success for us. We were able to improve our around 50% of the target that we had tackled, and when we were able to improve, the average improvement rate was above 106. This means that we weren't able to improve any target that we tried. It was due to sometimes misses of data or missing of controllability. But once we improved, and 50% is a big number, the improvement rate was sky high. Cliff found dozens of unique bugs. You know, Cliff is basically like a stress. You are stressing the rare functionalities that no other validation method is succeeding to stress. So it finds new things, and those are leading to new bugs. Cliff is in full production in many validation teams around Intel, using this solution almost on a weekly basis. So yeah, success. This was our first attempt to use machine learning for verification, and we asked ourselves, okay, so what is next? Do we have a new technology, machine learning? We saw it's going very well when we incorporate it with verification, but where do we want to take the next step? What do we want to do with it? So this leads us to the next step of our journey. So we became hungry for more, and we asked ourselves, where do we want to take machine learning and this technology? And we asked ourselves, what are the verification biggest problems that machine learning can help with? And I want to try to explain to you what I think the verification biggest problem of why bugs escape and why machine learning can help us here. And I'm going to try to explain this problem with this graph. This graph is basically showing you that as you add functionality to your design, your verification coverage space grows in an exponential manner. Meaning, if you add a bit to your design, you have twice as much states to cover, right? So in the 70s, where the chips were pretty small, we could have done directed tests, and this covered very well the chips. But as the functionality grew, as the design grew in the 80s, directed tests were just not affecting. Validation invented random testing, which was much more efficient in covering those sizes of chips. In the 90s, where there was another jump, random testing was not enough. Directed random was invented in order to make more even biasing of the random and help us cover the coverage spaces better. But when we come to these days today, and it's not just now, it's even 10 years ago, maybe even more, all those three methods together or on their own are just not enough. We have such a huge and complex design that we are just not able to cover all the elements of the design and find all the bugs. And this is due to two main reasons, right? The first one is inefficient testing. We have a lot of waste in our tests and our cycles. We run many cycles that just do the same thing over and over and not add anything to our quality. And the second thing is human dependency. We have a lot of misses in our understanding of the design, and we maybe don't write good test generators, and we don't do good definition of our verification goals. And the implication is obvious. Once we have missing coverage, once you have a hole, you'll have escapees. Any aspect in the design that you didn't validate, it will have bugs. So this is what we think is the biggest problem of why bugs escape, right? Is the fact that we are using 20-year-old or even 30-year-old validation methods in order to try to validate modern designs, which are so huge and complex that they are just not fit to this method. We need a new method. And we believe machine learning is the answer to this problem. And that is where we want to take machine learning. This is our conclusion. We want our machine learning-based solution to focus on faster coverage closure and expanding our coverage, to do bug hunting, stresses, exploration, find things that the human didn't think of. So now we have a vision. We know where to take our machine learning technology to. And so we came to our next step. Okay, we came to our management and told them, we have a vision. We want to put this program in place. We need two things from you. First of all, we need an investment increase. We need to understand this is not some Spartan startup thing like Cliff that we did on the side. This is a big program, a huge platform, and if we want to implement this vision, we need more headcount. The second thing is we asked our management to help us drive, to get commitment and the belief that this is the correct path to go to. And believe me, this is not easy. This is a very important step in the journey. I can tell you for sure that without management drive, commitment, and belief in this way, in this path, we wouldn't have gotten to the way we are today, where we are today. So we got all of this approved. We launched our program, and we started to implement our vision. And not soon after, we came to another success, which we call ITEM. And let me describe a bit what is ITEM. So ITEM is Intelligent Test Execution Management. And this is basically the first step in implementing our vision to do faster coverage closure. So its goal was pretty simple, to give us cost-effective regression. Give us maximum coverage, maximum buckets with minimum budget. Now, I don't need to explain this for what is coverage, but buckets, in a word, those are grouping of failures according to their failure signatures. So basically what we wanted is maximum quality with minimum cycles. Pretty simple. So let me show you some small illustration of how ITEM algorithm works. And you need to remember, this is all a journey of evolution. So ITEM was an evolution step on top of Cliff. So it derived many of the concepts, enhanced them, of course, and also introduced new concepts. So the first step in ITEM is obviously to take all the data from all our tests. And we are basically calculating the probability of each test to hit a specific target. Already here, you can see something new. Unlike Cliff, which only looks at rare coverage targets, now we can look at every coverage point and every bucket. So we have new types of bucket and a huge data space of targets. The next step would be to run pattern recognition algorithm. So again, this is based on Cliff pattern recognition, but it got much better because we had a lot of experience with Cliff, and we improved the algorithm in a scale. So it's basically like a new algorithm. And then we have a new table, the table that has pattern hit probabilities. So we have a huge list of patterns and for the huge list of targets. So this is not enough. We can't just run all their patterns. We have so many targets, it will take us years to run all the patterns. So we had to introduce a new step. This new step is basically to optimize the probabilities that we have and the patterns that we have to get an optimized list that maximizes the quality for a given budget. So at the end, we have a list of the patterns we want to run and the number of times we want to run each one. The ITEM solution flow is very simple. We start by running the full regression as we normally do in the verification process. Then we upload all our data to a new big data and AI platform that we built just for it. We'll talk about it in a minute. We run the ITEM regression. We can reduce the full regression size between 40 to 70%. And then we close the circle by evaluating the data that we have from ITEM and learn again and run the full regression back again. So the mode of operation that we've chosen is that every week we run the full regression and the next week ran only the ITEM regression. So basically every other week we save between 40 to 70% of our resources. Now the data set that ITEM is using is quite different than what Cliff is using. Here we are uploading the test metadata, which includes the test command line, the test name, the host, the runtime, and so on. All the test coverage, not just the rare events. Any information about the failure signature, the bucket, the bugs that are linked to it, and of course, all the test generator inputs, the configs, the sequences, and so on. And let me give you an example of item results. And this is really just one example because we have item running for many teams. But let's take one of the big examples. Item was running on one of the big core projects for around 2 years, and it was able to save up to 74% in the sizes of the list that we've tried, while keeping the quality and sometimes even raising the quality that we get. In total, we found dozens of unique bugs, even more than what Cliff has found, and this is on top of the uniqueness of Cliff. And we saved more than 5 million tests. This is a big number for pre-silicon verification. And again, as Cliff, item is in full production in dozens of verification teams. And again, as in Cliff, also in Alder Lake and in the latest under development CPUs. Now, important thing to mention about item, even though the original intent was to do a cost-effective regression, something that can save resources, we saw that we can also run item in a quality mode, meaning not just tell him to reduce as much as you can from the size, give it more budget, and then we get more quality because item is doing new things. It's trying to run new tests, and it finds uniqueness. So we'll give it more budget, we'll get more quality. This helps us a lot to find those dozens of unique bugs. And the success of item led to more evolution steps to follow-up solutions. And here are just 2 examples. We wanted to optimize also not just the full regression, but also mini regressions of 1,000, 5,000 tests, and also our gating regressions that are gating new design changes, what we call L0 and L1. And those are different solutions because they have different goals, different constraints, and so on. And they are all based on item and Cliff successes and their concepts, but they are quite different. So now we had a bunch of solutions, and we are putting our vision into place. But the scale up, and we wanted to scale up a lot. We wanted to go to more solutions and more verification teams. So let's talk a minute about scale up and the productization of solution. So scale up is not easy. For item, for example, we can consume 100 megabytes per test. Most of it is coverage, but not just. And this is just one test. If we have a regression, it can go to 1 terabyte. If we have multiple regressions, it's multiple terabytes. We are not learning just for one regression, but for multiple ones. And this is just one validation team. We have dozens of them. So this is now become multiple terabytes and maybe even petabytes. This can't hold by a small database. We needed a big data platform. And so our ITAI team built an AI cloud with the best-in-class methods and solutions in order to hold all those machine learning models, all this data, and give us all the recommendations. Now, productization is a key challenge. And I think when I look at the industry of machine learning solutions and how they become products, I think productization is one of the biggest pitfalls in machine learning. When we look at our validation, we have many problems, and we talk with our validators. They have many ideas of how to use machine learning, but taking an idea into a product, that's a huge question mark. And we've done that several times, so we have a lot of experience in that. And there are a few things that you have to look for. First of all, you need to make sure that you understand how you bring value at the end. An idea can be very good, very nice, but at the end, it might not be valuable as a product. You need to make sure you understand how to handle noise, both in the POC side and as a product. You need to plan correctly how to integrate all the things that you have in your solution. This is both in the human realm, right? We have a lot of teams collaborating here, both the AI team, the verification team, the automation team, and on the automation side, right? We have a different environment between the teams. We need to automate the entire process and make it something that the user can use easily. And 2 more very important things. First of all, you need to make sure that once you have a product, you have good interception to an actual project. We are not in Intel. We are not doing things just for research. We actually want to help our products, right? Our projects. So we had a few times when we actually had a product, but the interception was not good, and we had to drop the product. So this is a very important learning that you need to think about how you're going to intercept and who will intercept your product. And also very important is that you need to keep monitoring your product even after you deployed it. It's not enough to deploy it and forget about it. We had to monitor it, especially in machine learning solutions. You need to keep monitoring it every day. Even till today, we're monitoring every Cliff run and every item run. Okay, so we had a lot of solutions. We scaled up. We did a lot of productization. but it's important to say it's not all successes. And we had some failures, and I want to now talk with you about one of our biggest failures. And actually, it's something that Avi just talked 2 sessions ago. It's about triaging. Triaging and bucketing is basically the same thing. So let me describe the bucketing flow in press-recon verification in Intel. So in our flow of bucketing, we take every failure that we have in our regression, and we run it through a rule-based system, and we put it into a bucket. Then the debug team take the buckets, debug them in order to find the root causes. Now, the debug team, usually every debugger just choose 1 or 2 samples of that bucket because we assume that all the failures in the bucket are from the same root cause. So what is the problem with this process? There are 2 problems that we try to tackle. The first one is the merge problem, where 2 debuggers take 2 different buckets, but they lead to the same root cause. And this is an efficiency problem. One of the debuggers had a waste. The second problem is the split problem, where one debugger takes one bucket with multiple failures, which includes multiple root causes, but it only finds one of them because it's only debugging 1 or 2 of the failures. And this is already a problem of quality, because we can have an SKP to an upper level. Depends on how much rare the other root cause or how much time it takes to close the original bucket. And so we try to tackle this problem. First of all, we try to formulate it. Basically, we are trying to take n buckets and n root causes and find the mapping between them. The problem with this problem formalization is that we don't know what are the root causes. And therefore, a simple classification approach is just not applicable. We don't know the classes. Simple clustering approach is also not applicable. And why is that? This is because we didn't want to fully replace the rule-based system. We wanted to come on top of it. We wanted to make sure we preserve the human knowledge that we have in the rule-based system and just adjust it based on machine learning. And so clustering was not good enough. So I don't have enough time to talk about our algorithmic approach here, and you can contact me offline if you want to hear more. And we basically use the silhouette as a measure of cohesiveness. And we actually got it to be a product. We actually found value in it. We got it to be a product. There was a team that used it for around 6 months. But after 6 months, we had to drop it as a product. And there are 2 main reasons of why we had to drop it. First of all, as you heard from Avi, there are many challenges in trying to do good triaging with machine learning. You have labels data that because of human errors and missing labels. You have data challenges due to non-standard data sources and missing information. Human in the loop is the problem. We have a lot of differences in mode of work. And of course, it's very hard to understand what is the ROI, what is the correct impact. There is so much diversity in how teams are debugging. It's such a manual process that even if you find a solution, it might impact just 10% of the team and maybe 10% of their debug. So there is a lot of a big question mark on whether it's worth to invest a lot of time in doing such solution. And the second thing is that we started to see a big quality degradation in our results due to data changes. We just couldn't keep our finger on what was the actual change, what happened. We did a lot of analysis, but those 2 together really caused us to just drop this solution and put it out of production. And this is what really brought us to the next step in our journey, a reality check. We understood that we are not focused. We are too diverse on too many solutions. Some of them are not related to the vision. We had to keep focus. So that's what led us to do all the analysis and understand that debug is not for us. And it's important for me to say the fact that we failed to find a debug or a triage-based solution, just like Avi said, it doesn't mean that there couldn't be a solution. It just means that we didn't find a good solution. And just like Avi, I think that there is a lot of potential in placing machine learning for debug and for triage. But besides dropping the debug realm, we also wanted to focus on less solutions that are more focused on our vision, how we want to implement the vision and not move to side tracks. And so we come to a very interesting point in our journey. We just finished a big project, and we thought, what can we do on the next project? How can we take it to the next level? And we started to do some analysis, and we saw we are hitting a wall. And what is this wall? This wall, first of all, is some convergence in our solution. In our main solution item, we saw some convergence of it. We saw that it had a convergence curve, and you can't just keep running its recommendation over and over and get more quality. At some point, around 60% of the full regression size, you start to see a convergence curve. And this is not good enough for us. We wanted something that can give much more quality over time, even if you run it endless number of seats. The second thing is that we still saw a lot of things that item misses over the full regression. Even though item raises our quality by finding a lot of uniqueness, still the full regression had some uniqueness over item, and we wanted something that completely can replace our weekly regression or our full regressions. And we understood that we need to ask validation to change some of the methodologies. Till now, we didn't ask any change. We just told them, you're running list, just run this list. But we understood that the wall that we're hitting, we can't break it without doing some methodology changes in the validation side. And so we understood we need more analysis to understand what is the next step. This wall needs to be broken, and it's not just, okay, let's do item number 2. We need to understand how to do that and how to do it fast. So we got into analysis phase, and let me show you one of the biggest insights of our analysis. We wanted to look at what might make bugs escape, and where in those cases can machine learning help. So we took a few projects, and we looked at all the escapees that they had, and we put some categories on why did they escape. And for each category, we tried to understand, can machine learning help in this category? Green, it can help, red, it can't help, and yellow, maybe. So for example, you have the volume category where due to non-effective cycles, something escaped to post-silicon. You could have found it in pre-silicon, but you needed post-silicon volumes in order to find it. And this is definitely something machine learning can help with. And also human errors. Human errors is another category of why bugs escape. And so we looked at all of this data, and we noticed a few things. First of all the green ones summed up to 50% of our escapees. This is a very big realization for us. It's a very nice insight, because now we understand our potential. We understand where do we need to strive. Obviously, machine learning is not a solution for everything, but 50% is a huge number. So we understand our potential. The second thing, we understood which categories we should focus on, and the fact that we should focus on different categories in a different manner. So we understood the red ones are not for us, the green ones are for us, and we need different solution per category maybe. So we took all this analysis, and we reached our next step. We understood that it's not enough now to just give validation something from the side. We need to go AI and verification hand in hand together, helping one each other, and verification need to change a bit and need to change their methodology so they can help AI to help verification back. And this leads us to ML-oriented verification, meaning that the verification are doing things that are oriented for machine learning, and at the end, machine learning is using all this data and information and aids to help verification back. This is what I call empowering the machine learning. If you look at the two ends of our solution, they're trying to learn the connection between our stimuli knobs, the input to our test generators, and the functional coverage. But there is a huge gap in the middle, and this huge gap is encapsulated by three main black holes. The one is the test environment and the test generator, then the DOT, and then the output from the test generator that outputs the functional coverage. And the fact that there is such a long path between the stimuli knobs and the functional coverage sometimes causes us to have missing learning, and even cases where our learning is just not in good enough quality. So what we do in order to empower ML is to put those black boxes into a bit of white boxes. And it's machine learning friendly stimuli on the one side, machine learning friendly coverage on the other side, and DOT inside in the middle. So let's talk a bit about those and what we did with them. So machine friendly stimuli is talking about three principles. The first one is controllability. We ask verification to give us much more controllability in the test generator. So if till now machine learning can only control the number of sequences that we can run, now we wanted to control the types of sequences, the order of sequences, and more low-level decisions that the test generator is taking. The second one is visibility. We wanted to make sure we can see better what decision the test generator is taking and what are their outcomes. We can use this data in order to better learn their connection to the actual coverage sheets. And lastly, the relationships. We wanted to understand whether the test generator knobs have some dependencies, grouping, and so on, and this would help us analyze and learn better the connections. The machine learning friendly coverage is even a bigger change that we ask. We ask our teams, our memory IP, the execution IP, that for every coverage event, don't just write it as a one standalone event in the universe. tell us and tag us what are the building blocks that compose this coverage event. So make the coverage event a composed structure that we can understand its building stone, its building blocks, whether it's a register that you are using, a state element, a configuration of whatever. We want to understand the structure of the coverage event. On the other hand, we ask the teams to tag all those coverage events to features so we can understand the relationship between logical functionality to the coverage event. And now with all this hierarchy, we can analyze all that and understand this connection and get better solutions. We can give solutions that better tackle features and sub-functionalities, and we can also understand the composure of coverage events and understand the overlaps between them and analyze them better. Another thing that I want to mention about what we ask from verification is that we wanted to create some kind of a brain of all the data elements that are in the verification domain, whether it's coverage, feature, bug, a test plan, a command line, a bucket, whatever. There are a lot of data elements in the verification world, and we asked the verification to connect all the dots for us. And we wanted to use all those connections and analyze them to get better solutions. And so we did all that. We are working with verification to get all that. And with all this realization and understanding and definitions, we came to build our future solution. The future solution is machine learning-driven verification. It means that machine learning will drive all our cycles to get more effectiveness and better quality. Now, machine learning driven verification goals are two. First of all, you need to make sure every cycle counts. So every cycle that you run needs to add quality. You need to put the waste to the minimum, and then you will prove the bug to cycle ratio. The second thing is that you need to compensate over the human factor. After all, we are all humans. We are making mistakes. Sometimes the design is so complex that we miscomprehend it. That is fine, but we need tools to aid us and compensate over that. And machine learning-driven verification is the answer for that. Now, the realization that we've taken from the analysis I've shown before is that bug hunting is not one solution to fits all. It's not like that we can run item and find all the bugs in the design. There are different types of bugs, there are different types of features, there are different severities of bugs, and we need multiple technologies to hunt bugs. So for example, we'll need a coverage closure technology and a solution to find one type of bug, a missing stimuli technology and a solution to find different type, and exploration machine-based solution to find the different set of bugs. And so we started to build our platform and the architecture of a solution, and we had a set of or ensemble of solutions, but all our solutions are based on 3 stages. The first one is a target selector. So we thought that what is target in Cliff and item, we took it to the next level. So now target can be anything. It can be something that the project defined. It can be a heuristic, like all the rare event, all the specific functionality, and it could be something new, something that we take from the data. Something that we do as target mining or special heuristics, where we look at hotspot in the design or error-prone areas that we want to tackle, and we actually mine target using data analysis. The second thing is the pattern finder, which we already discussed. And this is, again, an ensemble of algorithms based on whatever we want to achieve at that point. And the third point is, of course, the optimization to find the best pattern to hit the targets with minimum budget. So the pattern finder concept was introduced in Cliff, and the optimization was introduced in Item. And this is basically another step in the evolution of all our solution. Now we have 3 steps that are very generic, and almost all our solutions are built on top of these 3 steps. And what differentiates our solutions between each other, the key elements are what targets do you take and how good they are, what test and data set and features do you select, and what is the value that you're looking for, and what is the cost you are ready to pay. And with that, we architected our solution, which is very simple in its manner. First of all, the layer of user-defined goals. We wanted to make sure that we have one API for user to define any goal that you want. It can be a low-level goal, like one coverage event or one bucket or one bug. It can be a function or a rule of these are the targets that they have. It could be a full space, like all the coverage events. Or it could be something more abstracted, an intent, like I want this feature or a cross of features or a subset of features. All these goals are going through our AI system where we run all our solution. And again, it's an ensemble of solution where per goal, it's trying to find the best and optimized test suite to hit those goals. And we have fully automated link with the verification environment where we pull our recommendation, run them, and upload the data back to the AI system. Okay, so we talked a lot about our journey, but the journey was not smooth. We had a lot of challenges. We discussed some of them. Let me try to summarize the challenges and learning that we had along our journey. So the first thing, and I think this is very obvious, data is everything. We had a lot of issues with our data, and we always need to monitor data and make sure we have consistency in the data. I'm sure you're all aware of that. Everyone that's using machine learning is aware that data is everything. Even when we saw in our analysis the data is missing, we had to understand what is missing and generate this new data. The second important thing is that we looked at the solution that we've made and productized, and we understood that when we have a good business process, it really impacts how our ability to introduce AI solutions. So for example, for Cliff and Item, those are test generation or regression optimization solutions. And since our verification environment is very stable in those processes, it was very easy to introduce AI. But when we got into the debug realm, this was a completely different story. There are no generic solution. There is no one platform. It's very individual. It's very manual work. It really impacted our ability to introduce AI. It was one of the reasons we failed. I mentioned this earlier. Management support is crucial. I can't emphasize this enough. We needed to do a lot of change management. At the end, a validator or anyone doesn't like to hear that the machine might do better decision making than him. So we had to gain their trust. So we did a lot of education, a lot of trainings. We were very transparent in what we are doing and how we do that. And we came with our results all the time to show that we are doing good stuff. And that gained our trust from the validators. And in the end, really helped us to deploy our solutions. And finally, it's very important to keep the human in the loop. Customer retention is super important. It was crucial for us to always keep in touch with our customers. So to conclude, I think machine learning is definitely a leap forward for validation, for verification. It's truly a game changer. We see it in every step that we are doing in our project in Intel, and it really impacts the way we do validation and verification. As I said, it's a journey of evolution. It's not something that you can start from the get-go in taking the best-in-class solution and trying to solve all the problems of the world. So our journey was long. You can learn from it and maybe take a shorter journey, but definitely it's something that you need to do as an evolution and try to understand how to incorporate machine learning that fits your needs. And definitely it requires faith. Machine learning is not trivial. It was quite a journey, but I have to emphasize, we are just getting started. We have so much we are doing now and so much we are looking forward to. The journey is just beginning. And as a final note about the future, in the last year or two, we see the vendors put in place a solution on their own and try to productize them. And as a strategy, we think it's correct to partner with the vendors and use their solution where we think that they are better than us. And this is definitely something we take as a point to the future. And we are definitely collaborating with them, even in the development of new solutions. And finally, I want to acknowledge the people in Intel that helped me put together this presentation from the Intel AI team and the Intel verification team. And with this, I'm done. Thank you.
Thank you, Tal. You hear me?
Yeah.
Yeah, thank you. Thanks a lot. Very interesting talk. So I will start with a quick question from your almost final message. You said that a human is important in the loop. And this wisdom, how to say, is against many of the other talks and many of other projects that we see that we want to take the human out of the loop in order to accelerate the MLCAD or in order to accelerate the chip design. So how do you see this? How do you see that? What do you comment on how much we need the human in the loop, where the human is really required in the loop, and whether we will be able to take the human from the loop when it comes to really, MLCAD?
Well, I think as I said, it's a huge difference between whether you try to find a solution where there is a human in the loop versus non-human in the loop. And currently in our solutions, we are trying to find cases where human is not in the loop because we find it much easier to first develop the solution and then productize it. As you saw in the debug, both me and Avi, when he presented it, when there is a human in the loop, it's much harder, and we both failed, and partially it was due to that. We don't want to completely remove the human from the equation, right? We don't need to replace our verification engineers with robots. But it's very important to understand that we want to make sure that the verification engineers use the time in the best way they can. We want to make sure that we do all the groundwork with machine learning, and they can focus on the things that machine learning can't do. And that is to understand what is the validation space that you need to look at, to analyze the spec, to be more creative in things that machine learning can't do. At the end, without the human experience, without the human knowledge, we won't be able to do the machine learning solution. They need this knowledge as a basic thing to count on.
Okay, great, thanks, clear. We have one question from the audience. So you mentioned you are running full regression every other week and running the item every the other week. What is your typical coverage rate between them? And he's asking, I mean, what level of confidence your item gives you? Is it if it is not meeting your expectation in each cycle, what do you do? Those are multiple questions.
Yeah, so our first productization of item was that we actually run it every other week. We still didn't have enough confidence in item, and we wanted to make sure that every other week we still run our full original regression. So even if item messed up and misses a bug, the full regression will find the bug a week later. So this was the way we started. Today we are in a different mode. We improved item a lot. We are all running it almost every other week, and our intention, of course, is to fully replace the weekly regression. Now we had very concrete success criteria for item on when is the quality good enough and when is it not. And we had coverage score that we had to meet. We had bucket scores that we had to meet. We had other quality measurement, and we always look every run, every period. We look at those metrics and measurement and make sure the quality is correct.
Yeah, makes sense. Thanks again.
I have a question. Yes. So first, thanks, Tal, for really great talk. Just two questions. You mentioned the size of the data. You said terabyte per day for team, and
yeah.
How long do you keep the data? What is the size of the data that you keep today? And the second is kind of related to it, because how big is the team that is working on it? We believe that there are no free meals, right? That there is this legend that you can take off-the-shelf machine learning algorithm, take some data and use it, and you see the magic. But we didn't see it. I didn't see it ever. So what is?
Yeah.
How many people are working on these solutions?
Okay, so those are two great questions. So let me try to tackle the first one, right? So data sizes. So we upload just for one of the validation teams, or it's several validation teams, up to 10 terabytes per month. Yeah, that's a lot. But we don't use all the data. It depends on the solution. Usually our solutions, since pre-silicon verification is changing so much, we can't use a year-old data usually to predict what the next week test will do. Usually we use 4 weeks length of regression, so 4 regressions or 5 regression backward. But we still keep the data a year back or 2 years back, depend on the solution. Some solution we do look a year back and look at all this data. So we have a good enough IT team to save all this data, but I'm saying that we are using this data per need. Usually the solution look 4 weeks backwards, okay? Now, for your other question, yes, this is a very good question that we are tackling ourselves also with. Does it worth to invest all the headcounts that we are investing? We have a big team. Yeah, we have a lot of people working on that solution, and we definitely will think it's worth it. I don't know if I can say the actual number of how many people are working on it, but it's not 1 or 2. Okay, so we have a big AI team that is working on that, and you need to understand it's not one verification team. We have many dozens of verification teams that are using those solutions. So when you go to this scale, it's probably worth investing more headcounts in your AI team.
Great. Okay, so thanks, Tal, again. Thank you for everyone, for all the audience, for staying long with us today. So we apologize for the technical delays. We are learning from this new platform. So Tal, many thanks for the talk and very inspiring. So thank you, everyone, and see you tomorrow for our last meeting and our last day in the MLCAD. Thank you.
And if you want to chat a little bit more, the social rooms are open. I know that we are a bit late, so feel free to join or to go back to your families.
Thanks. Okay, bye-bye.
Bye-bye.
Bye.